the way this unit works is I'm going to give you a brief overview of Newton's three laws, and then we're going to look at each one sort of more in depth, and regrettably that takes 4 whole days. Remind me next week is a short week, right? Yeah. Say again? Oh yeah. Then you go get a lecture. Then go outside and get a lecture. Just how they want it. Yeah, Friday is no school for you guys. Parent teacher day, right? So we're going to cover Newton's laws over the next 4 days. 1 day sort of as a general overview, and then each day individually. And then we're going to jump right into word problems. There's a lab as well. Generally, this unit's a little bit shorter. I would expect test early in December, would be my guess. Okay, so let's begin. Now, if again, as always, if you want to write these down, you can. There are certain things that are more important than others. Use your best judgment as to what you think actually needs to be recorded in your notes. So that's a skill you're going to need to have eventually. So, we're talking about Newton's laws. I guess if I go back to the first page, all it said was, there's Newton, he's got good hair. All the good scientists have good hair, right? Who said that? You're just used to agreeing with me, aren't you, Anna? You didn't think of it, what you were thinking, what you were saying. Or you, oh. Okay, so a force is simply a physical quantity that can affect the motion of an object. And it's a vector quantity. Now that's important. Why is it a vector quantity? Because it has a magnitude and it also has a direction. And I see everyone here is prescribing to the write everything down on the screen rule. Oh no, Jason's not. Good for you, Jason. It's a vector quantity. Why? Because it has a direction. Now that's important for you guys because it means when I ask for what the force is, you're going to have to include a direction. Now it might just be a positive or a negative, but it might also be a north or south or east or west or something like that too. Okay, so be aware. Generally, kind of the usual rule is, in general, if there's a direction given in the question, there's likely going to be a direction given in the answer. Have I said that before? I just did. So this dude here, Newton, was the first person to clearly describe the relationship between force, mass, and motion. And Newton's laws of motion not only apply on Earth, but are true throughout the universe. They are said to be universal. Okay, so if you're on the moon, Newton's laws still hold true. They are universal. Any of that important for test write-down kind of scenarios, do you think? No. Right? I'm just telling a story here a little bit. Moving on. Okay, now there are different types of forces that you are going to encounter. Do you remember what the 4 fundamental forces were? Gravity, electromagnetic, strong nuclear, weak nuclear, right? And all other forces are derivatives of those. And so these are not fundamental forces that I'm about to list. These are just sort of common everyday forces that occur that we have labeled because of those 4 fundamental ones. Okay, and they are a buoyant force, produced by fluids and act upward. I'm not sure why there's a funny bracket there at the end of that. What is a fluid? Anyone? Generally liquids, right? But they could also be air, gas. A gas can be considered to be a fluid. If you go on and you're taking engineering at the university, you're going to take like civil engineering, you'll take a whole course just in fluids and how they move and how they work. The elastic force is produced by stretching, compressing, twisting an object, right? You take an elastic band and you stretch it out, or you take a spring and you compress it. or you twist something, right? Even like a towel, if you twist. I'm trying to think of something smart to say, Colby, but I'm a little bit confused because you appear to be texting on one of the clickers.
Oh no, I'm just running my fingers over.
Oh, I see, okay, gotcha. Just makes you feel good? That, okay. You might want to. Electrical force is produced by the interaction between charged particles. You learned about this in grade 9, grade 10, right? You know, two positives repel each other, positive and negative attract each other. That'd be an example of electromotive force, right? When you rub the old balloon on your head, right? Electrical forces. You got your socks in the dryer that are stuck to your pants, and then you come to school with the socks stuck to the inside of your pant leg. That happens to everyone, right? Oh, does it? Just happens to me. Hey? Oh, don't get me started on balance sheets. Basically, you're putting a carcinogen all over your clothes every time you throw them in the dryer. You know why? Do you know why balance sheets work? Frictional force, produced when one surface moves over another, and it acts in a direction-resisting motion. Right? There has to be two surfaces in contact, and it always acts in a direction-resisting motion. Does there have to be motion for there to be friction? Yes? No. Yes? Does there always have to be motion for there to be friction?
No, because steel is
produced when one surface moves over.
Oh, correct.
But then why is it like you sit down and you stand up and all of a sudden you go touch someone and you get shocked?
Yeah, but is that friction or is that static? Like, if I just go push on this table, can I move this table?
Yeah.
Like, I'm big enough I can move this table, right? Well, what if I don't push very hard? Is there friction? Of course there is, right? That friction is preventing it from moving. So, Jason, you're right when you said, on the sensor it says produced when one surface moves over another. You're right about that. I should probably change that. Because friction only acts in a direction resisting motion. It doesn't have to be motion. Yeah. Number 5, gravitational force produced by the attraction of any two objects, and it acts downward on Earth, right? Again, these are all just common forces that you are going to encounter in the next year and a half of physics, because you're all taking grade 12, right? Excellent. Oh yeah, same period 2? Is there one more? There is. Magnetic force produced by the interaction of at least one magnet and another object. I had a magnet. Oh, I guess I do have a magnet, right? Right. So there's a magnet. Right. So there's a magnetic force between that and the board. The board is ferromagnetic. Okay. So again, I'm not going to ask you to list these. The only reason that I'm giving you this list is so that when you see them in questions, you'll go, okay, yeah, that's a type of force. So all of that writing that you just did was probably a big waste of time. You should listen to me when I say don't write everything down. Okay. Newton's first law of motion. Now, is this something? Does this feel like maybe, oh yeah, this maybe I should write down? Does it feel like that? I did trick you before. But this is kind of like this feels key to me. Newton's first law of motion. Now, you've probably heard parts of this before. Right? You've probably heard objects in motion, stay in motion, objects at rest, stay at rest. Okay, but that's kind of like the junior version. If there is no force acting on a body, it will continue in its state of rest, or will continue moving along a straight line with uniform speed. I'll let you get that down and then we'll talk about it. This is known as the law of inertia. Or the tablecloth trick, right? The law of inertia says, objects at rest, stay at rest. Coffee cups full of water, unless are acted upon by outside force, will stay at rest. Are you nervous sitting right there? You want some safety glasses or a towel? You might want to be a little worried. No, you'll be fine. You trust me? You think I've done this lots?
He's a professional.
I actually am a professional at this. No, actually that's not true because if I get, well, I guess I am getting paid to be able to drive. You're gonna be okay, you think? You're gonna be dry right there? Oh my, the first time ever I've spilled.
That's right. Do it again. I think
Just I am not lying. That's it, it's time to retire. That is the first time I've ever spilled.
It's gonna be me fault.
Well, I did notice that the paper had a couple of, did you see me doing that? I noticed there was a couple of, like, rips in it. You're gonna have to move it under the table now, too. Man, my perfect record is like toast.
Your streak is gone.
My streak is gone. I might have been a bit too long with the paper. Jason, I'm gonna move to your table, okay? I was gonna go that way. Because I got more room. Man, I can't believe that.
It's very slow.
Good thing Ashley is. Oh, I made it here.
Oh.
I think I did it right over there. There is a trick to it. Does anyone know what the trick is? Like there is an actual. Yeah, you actually have to pull down so that the table with the cloth goes straight across. If you pull at all, even if you think you're pulling straight, right, like this, like see how I've got a little bit of an angle there? That's going to spill it for sure. You've got to pull down. Not even a plot. Well, I did spill the first time. Who likes to play with water balloons? Oh, really? Yeah? No, this is a video. What the heck? Yeah, like I've never used Windows Media Player before. Oh. Let's see if you can only regurgitate it back to me, or if you truly understand what I've been talking about the last 10 minutes. Is this object moving? And is Newton, correct. The Newton is the unit of force, right? Yeah. Is this object moving? Well, it's just a yes or no question.
Excuse me, interruption. Mr. Churchak, come to the office, please. Mr. Churchak.
Well, you'll notice many of you said no, but you'll notice that I don't actually have a right answer, do I? What does your clicker say?
Submitted.
It says submitted. Because there is no answer. It depends. Was it moving before? You can't tell. Is it a coffee cup full of water at rest that has two people pushing on it for some stupid reason? Or is it something moving along with constant velocity? Like if you're driving your car into Oak River, Jason, right? And you set it on cruise. Are you driving at constant velocity?
Yeah.
Yes. Is there air resistance on you? Yes. Is there some force forward that the engine is producing? Yes. Are those two forces balanced? Absolutely they are. So the answer is, was it moving before? And if the answer is yes, it was moving, then it will continue to move. And if the answer is no, then it will stay put. So there is no real right answer. It's a bit of a trick question. Didn't count against you, did it? Okay, did anyone think that maybe that was a possibility? No, I got y'all. I wasn't trying to trick you. I'm trying to teach you. Sometimes I have to trick you to teach you. Okay, now what about Newton's second law? Newton's second law says the effect of an applied force is to cause the body to accelerate in the direction of the force. And I'll just pause there for a second. Okay, so let's unpack this a little bit here. What does this mean? The effect of an applied force is to cause the body to accelerate in the direction of the force, right? So if I've got my foam ball, my angry Pac-Man here, staying at rest in my hand, and then I apply a force to it, that's the wrong way to throw it, isn't it? There's still a full cup of water there, isn't there? He's getting paying attention. He's so excited about something, I don't know. You think the height of the cup had anything to do with it? I'm going to say it was those little imperfections in the paper. Colby, what's so exciting back there?
I was talking about rappers.
About the Raptors?
No, rappers.
Oh, rappers. Oh, you should talk about the Raptors instead. So, the effect of an applied force is to cause the body to accelerate the next force. If I apply a force, it accelerates. It goes from at rest to not at rest, to moving, right? What if I just roll it down the floor here, Hunter? And, oh, I ran into the table. What happened? Hey guys, I'm actually teaching here. When I ran into the table, what happened? The table leg applied a force to it, right? And it stopped. I'm going to try again. Without it hitting the table. No, don't hit the table. Let's assume it didn't hit the table. What would have happened? It would have slowed down. How come? I thought I was supposed to stay in motion. There's friction, and friction always causes problems with that first law. Always. Okay? And you should also know that the acceleration is in direct proportion to the force and in inverse proportion to the mass of the body. And I'm going to explain what that means right after you jot that down. And I'm also going to explain what this funny looking symbol is right there. For now, just draw it like that. The acceleration is in direct proportion to the force and inverse proportion to the mass of the body. Okay, so what do I mean by direct proportion? What does that mean? That's a math term. Trent, what does it mean, direct proportion? You know? No? If something's proportional. Okay, let me see if I can give you an example of proportionality. Okay? So think about, you guys are probably way too young. You ever, any of you guys ever play with little G.I. Joes and they're, you know, okay. And well, they're Barbies, right? Same kind of deal, right? Dolls, right? Whether they be male or female doesn't matter. But the clothes on them are proportional, right? Like G.I. Joe's pants fit him because they're proportional. He's a foot tall, his pants are like 6 inches tall, right? Just as, you know, Colby's 6 feet-ish tall. No?
He's 5 feet 5.
Oh.
I'm the Hobbit.
He's a hobbit.
Yeah, that's his nickname.
Are you serious?
Yes.
Yeah.
Why? Bilbo Baggins. He's a Hobbit. He's a Hobbit. You got big feet.
Too much info.
You got a big feet.
Anyways, right? So it's proportion. So direct proportion means if it's a big force, it's going to be a big acceleration. If it's a small force, it's going to be a small acceleration, right? And it's inverse to the mass. In other words, big mass, small acceleration, right? If you push with a certain amount of force on a really big thing, like this, right? Low acceleration, 0, right? Something really small like a deck of cards, I can move it. Small mass, that's inverse proportion. So the acceleration is directly proportional to the force and inversely proportional to the mass. This little symbol, weird thing here, means proportional to. Okay? That's what that symbol means. Now we're going to take that and we're going to convert it into a law shortly. Don't think I got anything else there. Okay. Oh, here it is here, in questions. Geez, I think I gave you the answer already. Hopefully you were listening. The more force, the more acceleration, the less the acceleration, the same amount of acceleration, or there is no relationship. I'm hoping everyone got it right. Almost. Yeah. More acceleration. Big, big force, big, big acceleration. That's what we're getting at here. Right? Hey, guess what question's coming next? The opposite one, exactly. The more mass, the more acceleration. The more mass, the less acceleration. Same amount, or again, no relationship. Hopefully you were listening. B, yes, excellent. The less the acceleration. Okay. A couple other comments about Newton's second law. If a force is applied to a body at rest, the body will begin to move. Just like when I threw the foam ball over at the cup and thankfully missed it, right? The foam ball was at rest. I applied a force to it, right? The body will begin to move, right? Eventually. You'll know when. Because I'll look at you and I'll go like this. If a force is applied to a body at rest, the body will begin to move, right? You're applying a force. You're causing an acceleration. By the way, I'm going to keep coming back to things and I'm going to keep repeating things. And I'm going to repeat them in slightly different ways because I'm going to say it over and over again and you're still not going to actually believe it. And some of you are actually going to get it wrong on the test. It happens every year. So if it feels like I'm repeating myself, it's because I am, and it's on purpose. If the body is moving in a straight line and a force is applied in the direction of motion, the body will accelerate. Really trying to show off by throwing it as hard as he could. Oh, big giant wind up like that. Try again. Okay, seriously, it's got to get to my hand for this next demonstration to actually work.
Yeah, not a base.
What did I do? If a body is moving in a straight line and a force is applied in the direction of motion, it will accelerate. Okay, actually, I did the third one there. Forgot to do that one. Okay. If it's moving in a straight line and a force is applied in the direction of motion, the body will accelerate. So if it's already moving, right? Let's try again, Manny. Try again. I had the wrong one in my head. Oh. I applied a force in the direction, and what did it do? It accelerated all the way over there into the box. Okay? This one here, if a force applied in a direction not in line with the motion, the acceleration will be in the direction of the force. When he threw the ball to me, and I whacked it that way and ended up at Mallory's table there, right? The acceleration was in the direction of the force. The acceleration and the force are always in the same direction. Is that what you were going to say?
No.
Oh, you should have. The acceleration and the force are always in the same direction. When speakers do this kind of thing with their hands, you know, Trump does a lot with his hands. He's trying to emphasize. Bill Clinton used to do it with his thumb, like this kind of thing, right? People that talk, they give lectures, they do things with their hands because that is a point of emphasis. And so I'm going to repeat it again, and I'm going to say, I don't even remember what I was saying. Oh, the force and the acceleration are always in the same direction. So if you're sitting in a big lecture theater with 200 people at the U of M, and the prof isn't writing anything on the screen, but he starts doing this with his hands, it's because he or she is to be sexist. He or she is trying to emphasize something, and you should write it down. There's a life lesson for it, not just a physics lesson. We got one more law to cover. We got 20 minutes. Oh, yeah. Okay, let's get through this as quick as we can. Don't write everything down, you guys. Don't write the important stuff. Reworking our proportional statement, we're going to get the equation. F equals ma. I'm not going to get into how we reworked it. You guys have seen that in grade 10, right? F equals ma, where F is in newtons, F is the force measured in newtons, N, m is kilograms, mass in kilograms, kg, and acceleration is in meters per second, and we talked about why it's meters per second squared. So Newton's pretty special because he has a unit, a physics unit, a quantity named after him. I think that's pretty cool. He's not. They've checked it. Combining the units for mass and acceleration, okay? Because mass is measured in kilograms and acceleration is meters per second squared. The true unit for force is the kilogram meter per second squared. And we've defined that to be 1 Newton. Okay? Newton didn't call it that himself. He didn't call it Newtons after himself. He would have called it kilogram meter per second squared. What if I was lucky enough to have a unit named after me? What would be my unit, Zoe? Yeah, if I had a unit named after me, what would it be? You don't know? Sarah, you look like she's smiling. She's thought of something, but she doesn't want to share it. No? Six Bennetts. What would that mean? 6 Bennetts of what? You guys are very disappointing. 6 Bennetts. I don't know how amusing that would be. That's just Christmas at my house. Newton's third law. Thankfully, there's only 3. Now this is the one that I sometimes get into arguments with kids about. One in particular comes to mind a few years back. When one body exerts a force on another, the second body exerts on the first a force of equal, and I'm emphasizing equal magnitude in the opposite direction. I'll pause and let you get that down. Okay, so let me explain this a little bit here. When one body exerts a force on another, the second body exerts on the first a force of equal magnitude in the opposite direction. So in other words, right, and you probably don't need to write this down all the time. This is more or less just for me as a reminder of what to say. Occurs all the time in nature. There's always an action-reaction. You probably learned this as there, for every action force, there's an equal and opposite reaction force, right? You probably learned that for grade 6 or something. For example, a book, I have lots of books lying around. Lying on a table exerts a force on the table, and the table exerts an identical force on the book. Right? So I got this binder sitting here. It's pushing down with about maybe 5 newtons. Right? Gravity's pulling down 5 newtons. It's pushing on the table 5 newtons. The table pushes up with 5 newtons. Every time there is an equal and opposite reaction force. Now the part that everyone always gets wrong is the equal part. And I'm going to ask you many questions to see if you actually understand and believe it. Okay? If you want to draw this picture, you can draw a weight force there and what's called a normal force, Fn there. More on those kind of pictures in the near future. You don't really need to do that. I'm keeping an eye on the clock, and I know that I want to show one more video at the end too. Here's the question. Let me remind you of this key word right here. Equal, which means the same. Equal. 50 newtons down, 50 newtons up. Are those forces balanced?
Yeah.
Is that book moving? No. But what if it was falling? What if we went on a field trip, Trent, and we went to the top of the senior center, the high rise, as we like to call it here in Gotham, and we dropped this book off the, we wouldn't do that, but why would Wade be standing, just hanging around the senior center?
I think he was hanging at grandma.
Oh, what's that? No, they're not that. But, would there be air resistance on the book?
Yeah.
Would that air resistance be equal and opposite?
Yes.
It wouldn't be equal? Would the book apply a force to the molecules? Equal and opposite. Eventually it comes to, I'm getting ahead of myself here, eventually it gets to a point where there's what's called terminal velocity, and it falls at a constant rate. Right? And then it wouldn't be moving, wouldn't it? More on that in a while. The table feels the downward push of your hand. What do you feel? Scared that the table has feelings.